So the whole point of NMR is to understand, right, nuclear magnetic resonance is to understand the connectivity of molecules. We're really going to start thinking about the connectivity. And that works with, in this case, radio waves. All right, radio waves. So radio waves, not very high in energy, right? So these differences, the way we're messing with these molecules, we're not using IR, right? IR shakes and bends bonds. We can see that. In this case, we're using just radio waves. So the way we do that, we do that with big magnets. Big magnets in really controlled magnetic fields. So essentially, what we have, they call these things, usually it's beta naught, there's a magnetic field. And an atom can exist in two states, alpha or beta. Beta's higher in energy, right? Basically what this means is your atom can either align with a magnetic field, right? It can align itself. It can be in the same direction as the magnetic field. Or it could be in a higher energy state in the opposite direction of magnetic field. That would be the beta state. So what happens is we hit a molecule with radio waves. That's enough energy to make that atom go from the alpha state to the beta state. And see how it's now against the magnetic field if the magnetic field is going this way? All right, this is the magnetic field. So the radio waves take a molecule and make it go from the alpha state to the beta state against the magnetic field. And then eventually it relaxes, right? It absorbs some energy, it relaxes, and that is what we actually measure. So eventually it goes back in line with the magnetic field, and we can measure at this point. So you can imagine this difference is different for different types of hydrogens, right? A different type of hydrogen will give you a different difference, different peak, right? But this is what we measure. We can increase this energy, this difference, we can increase, by increasing the magnetic field, we get a bigger distance here. So the bigger the magnet, the bigger the difference, the bigger, the more fine tuning you can see. It's like going into high def or 4K, right? The bigger the magnet, the bigger the difference is, so you can really tell, right, what's going on. You can really see those splittings. You can see all those peaks. You see all those fine differences. So the bigger the magnet, the bigger the difference here. So that level is the amount of theory I want you to know for NMR, what's going on. Now let's talk about what an NMR actually tells us. So let's think about the what we can learn from NMR, what NMR tells us, looking at a specific molecule. So that molecule is drawn up here. It's an ether. So whenever you're doing analysis with NMR, the first thing I would do is draw in all the hydrogens. So let's make sure we draw in all the hydrogens. So all the hydrogens are drawn in. What is the first thing that we learn from an NMR? What's the first thing an NMR tells us about? We've done all these. We have all these different types of hydrogens. It tells us, right? We have these different states, and every hydrogen has a different state. So it tells us about the types of hydrogens. So the first thing it tells us is how many non-equivalent, chemically non-equivalent H's, right? So that gives us the number of peaks, right? How many different types of hydrogens are in this molecule? So there's 3 types. So what I like to do is I'll circle them and label them. I'll label this A, these 2 B, and these 3 C. Good. What's the second thing NMR tells us? It tells us the relative ratio of H's in a molecule. Otherwise known as it does the integration. It tells us the relative ratio of these things. So right now we have A, B, and C. What's the ratio of those hydrogens in the molecule? What are the ratios to each other? Good. So the relative ratio here is 2 A's, 2 B's, and 3 C's. we make that any smaller? Nope, because we had to have whole integers. We could say it could be like 4, 4, 6, right? That's the same relative ratio, right? That's the same relative ratio, right? So that tells us, so now we know how many types of hydrogens we have. Now we have a good idea about the number of how many of those hydrogens represent. What's the third thing we're going to learn from NMR? The third thing is, are you shielded or de-shielded? Right, this is kind of tough sometimes. So shielded means you're shielded by electrons. But this gets a little confusing for people. If you're next to an electronegative element, so say you're next to this oxygen or fluorine, all right, let's draw in some lone pairs. Are you going to be shielded or de-shielded when you're next to an electronegative atom? You're going to be de-shielded. Think about it. Think about it in a little different way. These atoms are going to be pulling away electrons. Even though they have lone pairs, they're not, right? They're not sharing them. They're pulling away electrons. So actually A is very de-shielded. It doesn't have a very good shield of electrons because it's next to these electronegative elements that are pulling away electron density. So things that are near electronegative elements are usually de-shielded. Right? So near electronegative elements, you're probably going to be de-shielded. Right? Because they're pulling away the electrons. Or you don't have your electron shield. So in this case, which one of these is the most de-shielded? That's right. The most electronegative, the most de-shielded one is A. A would be the most de-shielded. It's next to both, it's near the fluorine and the oxygen. What's the least de-shielded? What's the one's the most shielded? C, right? Because it's the farthest away from the electronegative element. The only other thing about this, if you're de-shielded, where would you be at in the spectrum? Upfield or downfield? De-shielded, downfield. Which means higher numbers or lower numbers? Downfield means higher ppms. Good. Higher numbers. Excellent. All right, so the fourth thing NMR tells us, number 4, is what? It tells us essentially it tells us, really, who am I next to? What other H's am I near? Right? So we'll start looking for hydrogens that are 3 bonds away. What can happen is we can couple to those hydrogens. Think about these hydrogens as bells ringing. Right? These bells can hear each other. They can match pitch. They can couple to each other. Right? One bell, if it's 3 bonds away, one hydrogen can hear another bell 3 bonds away. They're going to couple to each other. Right? And that coupling is going to be distinct. It's going to be distinct. We're going to be able to look at that coupling constant. It's going to be distinct. So 3 bonds away. So let's look at a perspective of B. Or let's look at the perspective of A first. How many hydrogens are 3 bonds away from A? 1, 2, 3, 4. They're too far away. So A, right, doesn't have any nearest neighbors. So the equation is n plus 1. We call them nearest neighbors. So if you have 0 nearest neighbors, you have a 1. We would call that a singlet. If you have 1 nearest neighbor, it's a 2. We call that a doublet. 3, triplet. 4, quartet. Right? Singlet, doublet, triplet, quartet. Now, let's look at B. Let's pretend we're B. We're standing where B is standing. We're the bell B. How many nearest neighbors does B have? Other hydrogens that are 3 bonds away. How many does it have? 1, 2, 3. So it has 3 different ones, right? 3 plus 1, take your calculators out. Carry the 2. 4. Okay. 3 plus 1 is 4. Right? So that we would expect B to be what? We expect B to be a quartet. What would we expect C to be? C has how many nearest neighbors? 2. So we'd expect C to be a triplet. Very good. Okay. So now we want to, let's actually see if we can build this, actually draw an example of the spectrum would actually look like. So we know there should be 3 peaks, A, B, and C. So we know A should be a singlet worth 2 H's. Let's think about where should A be at, though. What actual ppm should we be at? So now let's take out your one of your sheets that you've been given about NMR. So to be able to answer the actual specific, right, we know this is de-shielded, right, because it's near the electronegative atoms. But the question is, well, what ppm would it actually be at? So to do that, we actually need to use, and what's that going to be? That's going to be a singlet at 6 then. So we'll just say 6 ppm, and it's a singlet, 2 H's, and this was HA. All right? So we said A was around 6 ppm because it has this oxygen and the fluorine pulling on it. What about HB? The HB we decided was going to be, what kind of splitting was HB? Quartet. Has 3 nearest neighbors, 3 plus 1. So this is a quartet. And it represents 2 hydrogens. What ppm would we expect this to be at? So we'll say approximately 3.5 ppm. And that's supposed to be a quartet, so what's that going to look like? So we'll say, okay, this is 3.5. Right, this isn't perfect, but I'm not asking you to be perfect here. Quartet worth 2 H's, and that represents HB. Nice. All right, the last one, so C. What did we say C was going to be split into? What kind of coupling was it going to have? Triplet. C was going to be a triplet. It has 2 nearest neighbors, HB. And it's worth 3 hydrogens. And what frequency, what ppm would that be at? HC. So HC right there. And it's going to be a triplet. It has to be worth 3 hydrogens. So I got to make this one a little bit bigger. So 1 ppm. This is worth 3 H's. And this is for HC. So that's what that spectrum could look like. So let's talk about coupling constants. So why does that matter? So we know HB and HC are coupled to each other. They can hear each other, right? They're 3 bonds away. And the reason we know that, besides looking at the molecule, we could actually look at the coupling constant. So the distance between the way these peaks are coupled, the way they're split, right? The way the bells hear each other, they match pitch. They affect each other in the same way. That's called the coupling constant. This HB got split, HC got split. They split each other. The way they split each other is the same. That's how we know they're coupled to each other. So if the coupling constant here is 8 hertz, so sometimes you'll see J equals 8 hertz. That's the coupling constant. What must the coupling constant also be? What must J equal for HC? 8 hertz, because they're coupled to each other. So that's how we know that those 2 hydrogens must be 3 bonds away from each other. See how we're starting to piece together this puzzle? So we know that they must be next to each other. If they are splitting each other, they can hear each other. We look at those coupling constants to know that. Our tables. All right, so here's one of the tables you always have. Identify first what we're talking about. So we're talking about an H that's 2 bonds away from Z. And Z can be an O, an N, or a halogen. Right? An O, an N, or a halogen. Well, we have that in this case, right? We have an oxygen and a halogen. But notice here, this is given as a range. So let's just think about, well, what would be more likely down at 2.5 of these 3 things? So if you pretend So instead of halogen, pretend it's a fluorine. Right? What's the difference between oxygen, nitrogen, and fluorine? Where are they at relative to each other in a periodic table? You're working across a row, right? So what's the major factor? Electronegativity, right? So which one of these would you expect to be closer to 2.5? Fluorine, nitrogen, or oxygen? The nitrogen, right? The least electronegative one. So if this was nitrogen, we expect around 2.5. If it was oxygen, we'd expect it around 3.5. If it's a halogen, right, I just put a fluorine in there, so chlorine and bromine or iodine, those are halogens, we'd expect it more around 4, right? Now this is additive. The one molecule we have has both a fluorine and an oxygen pulling on it. So where would we expect it to be around? I don't know, maybe 6, right? We're just guessing here, right? Because it has both a fluorine and an oxygen pulling on it, it's going to be pretty de-shielded. So maybe we'll guess it's around 6. What would HB be at? That had just the oxygen pulling on it, so we'd expect it's around 3.5, maybe the middle spot here, right? That's kind of the middle point. Let's see, what do these looks like HC? Is it near any pi bonds or near any electronegative atoms? Nope. It's probably down in this region, the saturated region, so let's just say 1.